This is STA 381, Chapter 2, Section 6. Okay, so we've been talking about different ways to find probabilities. Remember last time we talked about conditional probability. And so for this section, we will be looking at the intersection of events and multiplication and the total probability rules. Okay, so first of all, multiplication rule. So we did an addition rule a couple lectures ago, so now the multiplication rule says the conditional probability that we saw in the last lecture can be rewritten to generalize the multiplication rule, and that is as follows. Probability of A intersection B is equal to the probability of B given A times the probability of A. Also equal to the probability of A given B times the probability of B. So notice that we have both the probability of B given A and the probability of A given B, and that is just depending on what you're looking for. So if you are interested, if you have the probability of A, then you are going to end up using the probability of B given A. If you have the probability of B, then you're going to use the probability of A given B. So it's really just a matter of what information that you actually have in front of you. All right, so let's talk about what if your two sets are actually mutually exclusive. And so A and A complement are mutually exclusive. So you take a look, those are just the portions of the rectangle. And A intersection B, and B is the kind of kidney-shaped looking yellow blob. And so A and A complement are mutually exclusive, as I said, but A intersection B, take a look at where that is, and B intersection A complement are also mutually exclusive. And so B is actually made up of A intersection B union A intersection B complement. So you see, to find B, we take this and we union it with that. And that's going to lead to this idea of the rule of total probability, which says for any two events A and B, B is going to be made up of finding B intersection A plus B intersection A complement, as long as we are exhaustive over the entire sample space. And then this last line down here that I'm starring right now is just substituting. So our B intersection A is equal to, if you remember from the last slide, the probability of B given A times the probability of A. That's the first piece, plus the probability of B given A complement times the probability of A complement, and that's the second piece. All right, so let's go back and take a look at an example. So we have the probability is 1% that an electrical connector that is kept dry fails during the warranty period. And so that is a conditional probability. We need to keep that in mind and use that in a minute. If the connector is ever wet, the probability of failure during the warranty period is now 5%. So again, it's a conditional probability. If 90% of the connectors are dry, I think I left that out, so I'm going to just say if 90% of the connectors are dry and 10% are wet, what is the probability that the connectors fail? So we're looking at the overall total probability that the connectors are going to fail. So first of all, we have the probability of failure given dry is that 1%. We also have the probability of failure given wet. I'm going to call that dry complement, is equal to 5%. The other piece of information is 90% are dry, so the probability of dry is 0.9, and the probability of wet or dry complement is 0.1. And what we're trying to find is the probability of, the total probability of failure. Okay, so we're going to use that rule of total probability from the last slide, and it is located in your textbook. And so the probability of failure is going to be the probability of failure given dry times the probability of dry plus the probability of failure given not dry times the probability of not dry. So now we just need to plug our values in. 0.01, 0.90 plus 0.05 times 0.10. And you do the math and you get 0.014. So the probability that the electrical connector will fail is about 1.4%. Okay, that is the conclusion of conditional probability, this section, and we'll see you next time.